In the next subsection, I want to talk about mathematical induction. That is a strategy to prove certain statements that are true for an entire range. And it's often very challenging to prove these statements in a different way, whereas an inductive proof can be amazingly simple, to the extent that you've written down the proof and you still feel you don't really understand why it's true. But it's a formal and mathematically correct way to prove statements. It's very well spread, very well used, and you should definitely know about it. So what does that look like? First of all, it applies to quantified statements. So these are statements that talk about a whole range of statements, really. So we now have statements that have a parameter. It's not just a or b, it's a of x. And an example could be x is an even number. We have implicitly used that before when we were talking about the proof that, that n squared is odd and then n is also odd. We had the parameter n, and effectively we used it in this sense, but we didn't make it so explicit because the proof could just work for any number, any odd number n, and it was the same proof. We just had to pick a different k. Sometimes life is a bit more complicated, so here we want to explicitly say that it's a statement that depends on this number x. If we have such a generic statement, a family of statements, we can do two things. We can put an existential quantifier in front of it, and that's the statement that there is some value of x so that the statement is true. That's something we sometimes need. So you just have to find one example where it's true, then this statement is true. Exists an x so that a of x holds. The more complicated statement, but more useful one as well, is the universally quantified one, where you have this for all x. So this symbol is also called exists, and this is called for all. So that's the statement, no matter which value you give to x, a is true. And often people write things like this, for every x in r greater or equals 0, a of x, or something like that. So you often explicitly list the range of values for x that are allowed here. So if the statement only makes sense for non-negative numbers, you could write it like that. There's a formal equivalence between these two. If you have the statement for all x, a of x holds, that's the very same thing as saying there is no x so that a of x does not hold. Same thing, but again, sometimes proving one thing is easier than the other, so it's helpful to be able to flip around these negations. And what makes quantifiers really helpful in mathematics is that they can be nested to express fairly complicated statements. You might have seen this before if you've gone through an analysis class. If we have a function x and we say that as x approaches a certain value xi, this function has a limit of a. So the function approaches a if x moves close to xi. You can express this formally of saying for every epsilon that you're still away from a, so that's how far do you allow the function to be away from a? For every such accuracy parameter, if you like, there exists a delta. There exists a distance on the x range, so that when x is close enough to xi, namely closer than delta, also the function value is closer to a than epsilon. And here it's very important that these quantifiers are ordered in that way, because it means that delta can depend on epsilon. So that's the understanding. If you nest quantifier like this, then whatever comes inside can depend on all the variables that are further to the left. Okay. Good. Proof strategies for quantified statements. If the statement is an existential quantified statement, it's fairly simple. You just have to find an example that makes the statement true. Doesn't need a real strategy usually. It's just finding an example. It's more challenging for the all quantified statements. One thing we've implicitly done before in the n-squared proof was this. You fix an arbitrary but fixed value for x, and then you derive that a of x is true. That's what we did before. The other option is you use an inductive proof, and that's the new thing, so pay attention here. You prove two things. You have to prove that, so this is only possible if the range for x is the natural numbers, or it can be slightly generalized, but here let's pick natural numbers. Only the numbers 0, 1, well, maybe I should mention this. So that's the numbers 0, 1, 2, blah, 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 arbitrarily big, including the 0. You show that the statement is true for 0, and you show a different all quantified statement. You show for every n it's true that if a of n holds, then also a of n plus 1 is true. And that's the inductive step. It's a bit like climbing a ladder. You start with a0, that's the first part, and then you apply the inductive step to get from a0 to a1. Because if you set n to 0 in this statement, you have an implication a0 implies a1. But we know a0 is true, so it implies a1. But a1 then implies a2, and you can climb all the way up to infinity. Not physically, but in terms of a mathematical proof, this is a valid step to do. There's slight generalizations to this. Instead of just using the last statement, you can use all previous statements, so all the statements with the parameter smaller than n, and show that that implies the next statement. And you can generalize the idea of induction a little bit to other sets and other discrete objects. We won't make massive use of this, but it's worth mentioning at this point. Now, you will see in the tutorials another example of how to use inductive proofs. You might have seen classical examples like this in discrete mathematics classes. You will have some chance to practice this a little bit.